In this video, I want to talk about limits of a function of two variables. So here's an instance of what that means. You have a limit, and instead of just a single variable like x going to a certain value, you have a pair of values going to a point in the plane. And there is a lot of introductory stuff to explain about these problems that I'm not going to do in this video, and one reason that I'm not is because this other person has done it so well that I really don't think I can do any better. And if you Google limit of a function of two variables and watch this video, this starts with the very beginning, and the exposition is very good. So I highly recommend this video. So I'm not going to be doing introductory things, and if you're confused by some things that I say, you might want to watch that other video first. But I want to evaluate some sort of hard limits, or harder to evaluate limits. And for the first two problems that I'm going to do, I'm going to be using the Squeeze Theorem. And in both of these cases, it's going to turn out that the limit of this function exists and is 0. And then I'm going to look at this function, which is really challenging. It turns out that the limit does not exist for this one, but the argument is kind of hard to stumble on. I've spent a lot of time thinking about this one, actually. So let's get started. So I'm going to work on a little notepad and just do the things that you always do when you try to evaluate these limits. I'm not going to go, like right to the end, because the trick that works didn't come in a flash of insight. It came from doing these little scribbles. So let's go over to the pad here. And what was the function that we were looking at on the other screen? It was y to the fourth power over x to the fourth plus 3y squared. And you want to find the limit of this thing as x and y go to the origin. So the way you do these problems is you start to explore different ways that x and y could go to the origin. I'm sorry, my handwriting is so bad. But so here is an overhead view of three-dimensional space, and it should be the case that the surface defined by this function is sort of floating above this picture. And it should be the case that no matter how we go to the origin, as long as we go to the origin in a nice continuous, doesn't even really have to be continuous, it just has to go to the origin. So as long as we follow a path that goes to the origin, it should be the case that the limit of this is the same. So if we go that way, it should be one thing, and if we go this way, it should be the same thing, and so on and so forth. Okay. So when you start to do these problems, the first thing you want to do is see if you can plug in. And in this problem you can't plug in, because if you plug in 0 and for both x and y, you get 0 over 0, which is undefined. So the next thing to try is to approach the origin two different ways and see if you get two different numbers, and then if you do, you know that the limit doesn't exist. So let's try that. So the easiest thing to do is first to approach the origin from on the y-axis. So let's try that. So what does that mean? That fixes x as 0 if you're just restricting yourself to the y-axis. And if x is 0, then what does this become? This becomes y to the fourth power over 3y squared, which is the same thing as y squared over 3. Now you can ask yourself, what does this do as y goes to 0? And it goes to 0, right? So if I approach the origin along the y-axis, what I'm getting is 0 is the limit of this function. What about approaching 0 on the x-axis? So we should see if we get a different number. And so what does this mean? Well, if you stick on the x-axis, it just means that you're setting y equal to 0. I have a feeling you can't see that very well. So it means that you're setting y equals 0. And so what happens in this expression if y is 0? Well, if y is 0 and x is non-zero, then this whole thing is just 0, right? So it's 0 if y is equal to 0 and x is anything other than 0. So the limit as you approach the origin here along the x-axis is also going to be 0. All right. So that's a sign that the limit might really be 0. So there's some more sort of crazier paths that you can try, and the more paths you try and get the same answer, the more confident you become that the common answer for all those approaches might really be the limit of the function as the point goes to the origin. Let's try a couple more, because actually proving that the limit is such and such can be challenging, so it can be good to explore a few possibilities before you do that, because that approach involves actual thought, which is always hard. So if you set y equals mx, then what are you doing? Then you're considering all the paths to the origin that are lines of some slope. So this would be a line through the origin with slope 1, so this is just sort of the m equals 1 case of this expression. And then if you go along a path that's twice as steep, this is sort of the m equals 2 possibility. So just by leaving m as m, you can consider all these at the same time. The only one that is not considered under this expression is the case where the slope is undefined, and that's the vertical line. But we've already considered that separately. That's just the y-axis. All right. So let's do it. So what you have to do is you have to substitute mx in for y into this expression. So what happens if you do that? You get m to the 4th times x to the 4th on top, and on the bottom you get x to the 4th, and this becomes 3 times m squared x squared. And what's going to happen to this thing as x goes to 0? Well, let's get rid of that x to the 4th and things will be more clear. So multiply both top and bottom by 1 over x to the 4th, and then on top you get x to the 4th power, and here you get 1, and here you get 3 m squared times x to the minus 2. And now what happens to this thing as x goes to 0? So as x goes to 0, the thing that you really have to focus your attention on is this, which is 1 over x squared. And as x goes to 0, this thing becomes like 1 over 0, which is infinity. So as x goes to 0, this expression becomes sort of like, 1 plus infinity is still infinity. It becomes something like m to the 4th power over infinity, and that's just 0, right? So it's something over a really huge number is 0. So what we just showed is that even if you approach the origin sort of along any line, it's still the case that the limit of this expression is going to be 0. Now that's not a proof that the limit really is 0, but it is evidence. Now that we have some evidence for the guess that the limit really is 0, let's try to prove that it is. And I'm gonna use the Squeeze theorem, and I'll say more about what the Squeeze theorem is in Sage, because I can draw a picture and make sure I can get this forward here. Okay, so let's take this down. Right. And so there was a 4th power. Let me put that back. So I'm going to start like this. This is an approach they take in the book that frequently works. Sort of start with the numerator, and I'm going to start with y cubed. And I know that's going to seem bizarre and coming out of nowhere, and that's one reason these, actually proving that the limit is such and such is kind of challenging, because there's no one approach that always works. You just kind of have to think hard and do a lot of them and get some experience. And so I claim that y cubed is less than or equal to this when y is close to the origin. So by that I mean the absolute value of y is less than 1. So just convince yourself that this is true. So x to the 4th is just some positive amount, and what I it's also true that when this is true, y squared is actually greater than y cubed under these conditions. So see why? Because if this is small, raising it to another power just makes it even smaller. And so that's why this inequality is true, because here you have something bigger than y cubed times 3 plus a positive amount, so all that is bigger than y cubed. Right? Now we have this. And so what I'm going to do now is divide both sides by this, and that's kind of a standard trick, I guess. So then you get y cubed over this stuff. And by the way, so I picked that stuff to be the denominator of the function that we're interested in, so that's not a coincidence. So this is less than or equal to 1, right? And now I'm headed for, what I'm trying to do is get, some kind of inequality involving this expression. So I'm almost there. The only thing is I'm missing a y here, and I left that off on purpose. What I want to do now is multiply both sides by the absolute value of y. And if I do that, then I get y cubed times the absolute value of y over x to the 4th power plus 3y squared is less than or equal to the absolute value of y. Okay. And this is just the same thing as y to the 4th power. So I have my original expression back. So I have y to the 4th power over x to the 4th plus 3y squared. And that's what I started with, which is good. And this thing is less than the absolute value of y. We've shown that. This is for small values of y. And notice that everything here is positive unless it's 0. So it's less than or equal to 0 for non-zero values x and y. And so what have we got here? We've got like a squeeze situation. So this is a function of x and y, this is a function of x and y, and this is a function of x and y. So in the small circle around the origin of radius less than 1, this inequality is going to be true. So if I draw sort of the unit circle here, inside the unit circle, these inequalities are going to be true. So that means if I approach the origin and along any path, this part is going to go to 0, right? It's just clear that as the y coordinate approaches 0, this thing is going to go to 0, and this thing already is 0. And so what happens is the thing in the middle gets squeezed down to 0. So this is squeezed to 0. And this is the end of the argument, but let's look at the picture. So I have this code up here, and let me just load this. Maybe Sage will behave itself. And we need to actually look at the plot. So let's look at my plot. Okay. Alright, and this is a picture. So the blue Pringle in the middle is the function that we're interested in. And this V shape is the absolute value of y, and this green thing on the bottom is the function z equals 0. So you've got z equals 0, z equals the absolute value of y, and the function is trapped in between. And you can see that any approach to the origin is going to pinch the blue Pringle between these two green sheets, both of which are going to 0. So by the squeeze theorem, the limit is 0, and we're done. We're done with this problem. Wow, so that took a while, huh? Let's go on to the next one. All right, so I'm going to apply the squeeze theorem to this. And maybe just to move along a little bit more quickly, I won't try the things that turn out not to work. So, but I would ordinarily, try to approach the origin along at least any line. So first try the x-axis, the y-axis, and then try it along any line. So all those things give the same answer, which is 0. So I'll just take that for granted and go right to the part where we prove that 0 really is the answer. So we're trying to find the limit as x, y goes to 0, 0 of x squared sine y squared, and the denominator is x squared plus 2y squared. Okay. Alright, so what's the argument here? So I'm trying to take something from the numerator and make an inequality with the denominator. So let's just try this. So is this true? It is true because x squared and x squared are equal, and this is going to be a positive amount, so this inequality is true. Now divide both sides of the inequality by this, and you get x squared divided by x squared plus 2y squared is less than or equal to 1. Okay. Now you can multiply both sides of that inequality by the missing piece, sine squared y, and what you get is the original thing that we were considering. The original function is stuck between, so it's less than or equal to sine squared y, and that comes from multiplying both sides of this inequality by sine squared y. But it's also bigger than 0, and that's because you've got a positive number over a positive number, unless you've got 0 over 0 where it's undefined. Right, and so now what happens, we can just ask ourselves what happens to these extremes as x, y goes to 0. So as y goes to 0, this goes to 0. So this goes to 0 as y goes to 0. And this thing already is 0, so you have the middle part, again, is squeezed to 0. Squeezed to 0. Okay, and that is the argument. I haven't written everything out, as nicely as I should have, maybe. Let's look at the picture that goes along with that. So I'll load this, and this will actually make the plot. And here we go. So this picture is kind of really pretty. And can you identify these green things? So this is just a little part of z equals sine squared y. So this shape, it looks like a parabola, but it's not. It's z equals sine squared y. And on the bottom you have the function z equals 0. And around the origin, this function that we're concerned about, whose graph is the blue surface, is trapped between those other two surfaces. And so as you approach the origin in the plane, where you go on the blue sheet is bounded above by z equals sine squared y, and it's bounded on the bottom by just the xy plane. And so by the squeeze theorem, the limit is 0. And that's the end of that question. Now let's look at this thing. It's caused me a lot of pain trying to figure out what's going on with this. So you have x times y to the 4th, and on the bottom you have x squared plus y to the 8th. And one thing that makes this kind of hard is you try all the natural things, you try all the lines through the origin, and the limit is 0 for all the lines through the origin. Then you try, I don't know if you noticed up here where I define this code, maybe you can pause it and look at it if you're really curious about where this red line comes from. But this red line is what you get when you follow a parabola. So this is y equals x squared. So if you approach the origin along the parabola, the limit is still 0. And it kind of seems like as you approach the origin along this crest, something might happen. But then in this picture, it sort of settles down, and it does go down to the origin here, and it looks like it might be smooth there. If you look at a different plot, a plot that you get using the Google 3D function plotter, let's see if this thing is kind of cropped out. Let's load it again. So this one, makes you worry a little bit more. So sure, it's still going down to the origin at the last second there, but it's also got a hole in it, and it looks like it might be doing something weird. So this is a case where the graph is really sort of inconclusive, and we have to, get out our pencils and do some analysis. So it took me a while to figure out how to sort of break this thing. It turns out that the limit as y approaches 0 does not exist. Let's do the argument. Let me see if I have this function written down already. I should, right? Okay, so let's go over to this and get some space. And let me copy the function down. The function is x times y to the 4th power over x squared plus y to the 8th. And we want the limit as xy goes to 0, 0. Okay, so you can try some things here. You know, try y equals mx, and you'll see that if you do this, then the limit is 0. You can try y equals m times x squared. You know, this is a parabola where you can control the width with m, and if you try that, you'll see that the limit is 0. And if you try to come up with some kind of inequality argument, you'll fail every time, and the reason you'll fail is because it's not true. But you can try several things and try to get those to work. So the thing that does give you some insight is if you set y equals m times x to the a. So now I'm trying to sort of just, it's a power function. So is it true that if we approach the origin along any power function, the limit is the same? So let's make this substitution and see what happens. Then on top we get x times m to the 4th, and this becomes x to the 4a, and on the bottom this is x squared, it just stays x squared, and now this becomes m to the 8th power, and we've got x to the 8a. Alright, and just to make things a little bit more clear, let's try multiplying top and bottom by, oh, by the way, so these things combine. I'm going to do that so that things are a little bit more clear. So let me combine these two x's in the numerator before I do what I was about to do. So on top we get m times x to the 4a plus 1, and in the numerator we get x squared plus m to the 8th power x 8a. Okay. Now I'm gonna take out all the 4a plus 1s. So I'm going to multiply top and bottom by x to the minus 4a minus 1. And so the point is that it will cancel that thing in the numerator. And I'll do the same thing down here. And on the top you just get m. So that's sort of the point. Oh, it's m to the 4th, isn't it? That doesn't matter. But so in the top, m to the 4th gets left. And on the bottom, what happens here? You get 2 minus 4a minus 1, and so you get 1 minus 4a. So this is x to the 1 minus 4a plus m to the 8th just hangs out. I'm going to give myself another page. And here this comes in, so I've got 8a minus 4a minus 1. So this becomes x to the 4a minus 1. And so does this help? So now you just sort of have to observe that if you make a equals 1/4, then something interesting happens. This becomes 1 and this becomes 1, because 1 minus 1 is 0 and 1 minus 1 is 0. So if I look at the particular power function, you know, this is sort of y equals m times the 4th root of x, then something interesting does happen. On top you get m to the 4th power, and like we've been saying, this becomes 1, and this becomes 1. Okay. So now we have an expression that doesn't have x and y in it at all, but the value depends on m. So if m is equal to 1, this is equal to 1 over 2 is 1/2, but if m is equal to 0, then this is 0. So by changing m, you're changing this route along which you approach the origin, and as you make those changes, you're getting different limits, and therefore the limit does not exist. because you can approach the origin two different ways and get different answers. So this is D and E. So that one was kind of hard. I'm going to stop the video,